Hey folks, we're going to use Ampere's law to figure out the magnetic field strength caused by coils of wire called a solenoid. And I got a picture of a solenoid there. We're going to draw that out, don't worry. But that's what it would look like. Now you'll notice, and this is the ones like the ones we have in class, it's copper wire, which is not magnetic, all right? And everything else here is plastic. So there's nothing magnetic about this. But when you run current through it, it becomes a magnet. And you have probably done a little experiment with something like this before when you've wrapped wire around the nail, let's say, and you run current through it and it became a magnet. So basically, this is going to become an electromagnet when we run current through it. Now, I have a couple demonstration videos that show this being an electromagnet and also shows which end of this becomes the north and which end of this becomes the south. I will kind of walk you through that right now as well. So let's say our solenoid is, if you look at that, I'm going to draw it upright. So it looks like this. Okay, so it's a cylinder. Okay, and it's got wire wrapped around it. And we can wrap the wire like that. Okay, so if you would take a moment to sketch that out. And we'll say the current's going that way. So I'll give you a moment to sketch that out. Okay, now that coil makes a magnetic field. Now you can use your first right-hand rule that we've been using all along so far to figure out which way the magnetic field goes, but there's a second right-hand rule which is the opposite of the first. The first rule says, hey, your thumb, you put it up against the wire in the direction of the current and your fingers curl with the magnetic field. That's because for a straight wire, your current's going straight and your magnetic field's going in a circle. Well, this here's the opposite. Here we've got the current going in a circle and our magnetic field's going to go straight. So you just reverse those two things. So if you imagine holding your fingers and curling them in the direction of the current, and which way is your thumb point? Well, it should be pointing up right now if you're actually trying this out. So what ends up happening is there's a magnetic field. That thumb represents the magnetic field direction of the field inside the solenoid. So that is our magnetic field inside the solenoid. And your thumb also points, this will be the north pole of that solenoid, and this will be the south pole. Okay, so it all depends on how your fingers are wrapped around which way the current's flowing. If the current were flowing the other way, your magnetic field would point down instead of up. Now, I'll make a note here. There is a much weaker field that goes around like this, but it's very weak compared to the field inside the solenoid, so we pretty much ignore that. Now, how do we figure out the magnetic field strength inside that solenoid? Well, we're going to use Ampere's law. Okay, so we've got integral of a closed path B dot ds equals mu naught In. Okay. Now, the path we're going to take, this gets a little tricky. So remember, we want the path to either be parallel to or perpendicular to the field, depending on the path, and you want the field strength to be the same everywhere along the path. Well, it turns out for a solenoid, the best path to use is a rectangle. Okay, so there's my rectangle, and I'm going to give it dimensions. I'll call this the width, and I'll call this the length of the rectangle. Okay, and there are four sides to that rectangle. I'll label them A, B, C, and D. All right, well, let's start with B and D. So the way we've drawn the rectangle, at both B and D, the magnetic field is perpendicular to the top and bottom of that rectangle. So in that case, if you were to do B dot ds just for those two sides, you'd get 0 because there's no part of the magnetic field that's parallel to that path. The dot product would be 0. How about C out there? Well, C is where the field is very, very weak. Okay, so there might be a little bit of a dot product there, but because the field is weak out here, we pretty much ignore that. The field is relatively close to 0 compared to inside the solenoid. So this makes this really simple. Your path, the only part of the path that gets a dot product is path A. So that is just the length of that times the magnetic field. equals mu naught. Now the one trick here is what's I in? Well, what you've got is you've got this field, or you got this current poking into the rectangle at basically 3 spots. 1, 2, 3. There are 3 currents poking through that rectangle. So what we say is we say N, the number of loops poking into that rectangle, times the current in each loop. So that's pretty much it. Your magnetic field is mu naught N over L times the current, okay? And N over L is, I'll kind of write this over here, N over L is the number of loops per meter, okay? Number of loops per meter. So like if you look at the solenoid here, if you were to probably count the number of loops in a centimeter, then multiply it by 100. So there might be, 20, 30, 40 loops in a centimeter, and then you multiply that by 100, you get, whatever, 2, 3, 4,000 loops per meter, okay? So we often will call this, oops, sorry about that. We'll often call this little n, which is the number of loops per meter. So you can rewrite this, B equals mu naught little n times I, okay? Notice something else about that field. Within the solenoid, that field is fairly constant. You'll notice within the solenoid, I've drawn the field lines roughly equally spaced. That's not an accident. So that is your magnetic field inside the solenoid. And you can make a very strong magnetic field if you have a lot of turns of wire. And also, you can make it even stronger still if you put a piece of iron in here. Iron or any other metal will make the magnetic field stronger in there. All right, so I hope that video was helpful, and thank you very much.